So, hi, my name is Anton, and I want to talk about small data. I feel a bit odd because everybody talk about big data and machine learning, and here I come in saying, oh, look at small binary files. Okay, so a bit about me. I work at a company called Transit App. Oh, it's a bit distorted. I'm sorry for that. I hope it's still readable. So Transit App is, well, it's a transit app. It's really distorted. It looks prettier if it's not so distorted. And basically what the app does is you open it up and it tells you what's nearby in terms of transit. It basically says when does the next train go or the next bus or all of these things. So it's like a way to get around. If you open up the app, that's basically what you see. And one thing that I work on is making sure that when this shows up, it's really, really fast. Like you basically open it up, it's pretty much immediate. And the way we do this is with our approach to data. So usually when you design an app like that, that shows something like a schedule, you would have the app just as a thin client to some servers on the web. So basically the app comes in and says, okay, the user asked me to show something, so can you tell me what's nearby? So then the server comes back and says, well, here's a bunch of schedules, here's what's gonna depart soon. So then the app says, oh, thank you, and it shows it to the user. And our approach was to have the server send a full set of schedules to the app. And then the app can say, well, I need to show something to the user. Well, now I actually have the complete set of schedules. I don't have to go ask the server. I can just answer this question myself right now. So if you open up the app right now in Berlin, it will download the complete schedules on the first load. That's the complete schedules for Berlin and Brandenburg of everything. So that sounds kind of crazy, but it works. So the advantage of this is it gives us a better user experience. For one, if you open up the app or you move around on the map, you basically can answer the question what's there immediately, because rather than going to a server, which may take some time, you might be on a bad connection or whatever, you just have to open up a file, you have to look into the file and get the data out of that. But it also means that it works offline, which, it's an app that is for users that take the subway. Sometimes on the ground you don't have a connection, so sometimes it's actually pretty convenient. Also, it's for people who travel, so if you go to another city, you don't have a data connection, you can still use the app. So that's kind of neat as well. But also it means for us, for our infrastructure, that our server doesn't have to answer every single request from the app. There's basically no load on our servers, because only when the app hasn't downloaded the data yet, does the app make a request to our servers and say, okay, what's nearby? It has to do this because you can't just assume that you can always have the data available and download it. But overall, we can have like millions of requests served from our server because our server doesn't serve most of these requests. They're served within the app. So the problem with sending whole schedules to a device is that the schedules are actually pretty big. So I took a quick look. The schedule for Berlin, that's the VBB schedule. I don't know whether that means anything to you. That's basically the transit association covering all of Berlin and Brandenburg. It's about 26 megabyte file. For Montreal, just the metro and the buses is about 44 megabytes. So that's a lot of data. If you're on a connection that's like 3G, that's like 200 kilobits, that's like a slower 3G connection. If you would download that file verbatim, it might take like half an hour. That's way too long. So we have a special binary format that also includes a bunch of compression, where these files get much, much, much smaller. So for the Berlin data, it compresses down to about 2 megabytes. It's about a tenth. For the SDM data, it compresses even further to about half a megabyte. That's about a hundredth. So now we have a bunch of data that's basically the size of a large image file or a website or something like that. So now you can download this data without even asking permission to the user. You don't have anything that says, oh, would you like to download the schedules now? It just does it. You don't even notice it. You don't even know it. I think most users of our app don't even realize that the schedules are available offline. So in order to do this, to understand how this is done, well, maybe I should mention how transit data is usually stored. So transit data, which it's like a detour to something that maybe is a bit strange to some people, but anyway, transit data is stored usually in a format called GTFS. It's a format that Google came up with together with a transit agency called TriMet. It's basically a zip file that contains a bunch of CSV files, and these CSV files act like a database. It's like a dump of their database. But this format has evolved as being the standard, and it's used all over the world. And we get this data for several hundred agencies all over the world in this format. So if you look at it, the Berlin feed, which I just named VBB-zip right now, inside it you'll have these bunch of CSV files that are actually labeled as text files. So since it's a zip file, if you uncompress all of these text files, they're actually 250 megabytes big. So already the data is compressed, right, at 26 megabytes. And you have text files. One is called stop times, which is basically just for every trip in the schedule, it says for every stop that the trip passes by, what time does it pass by at that particular stop. So that's basically all of the numbers that are in the schedule. Then there's a list of all the trips, a list of all the stops, a list of all of the routes, and it has all of the data associated that you need with it. So the way I looked at the data is to say, well, the stop times, the actual schedules, this is like a bunch of numbers. That's like numerical data. And all of the other data that basically tells us what is the structure of the network, what are the routes, where do they stop, where are the stops, and all of the stuff. I sort of consider that more like structured data. If you store it, it would be like a giant tree or something like that, or like a database where things refer to each other all the time. So if you want to make this data smaller, naturally, because the stop times are so large, one would look at the stop times first. So if you look at the actual stop times file, it's basically a database-looking thing. A huge text file that is incredibly verbose, where every row is basically one particular data entry, one particular time, like an arrival and a departure time at a particular stop for a particular trip. And you also see the stop sequence numbers. So for every stop that the trip makes, it goes and has one of these entries. It's like, that's not how I would think about a schedule, but that's what they do because it's basically a dump of the transit database. The way I would look at a trip is more like this. This is actually, I just downloaded this yesterday for the M10 tram, which passes by here at some point. So this is also a schedule, and this is much more compact. So here you see every row is basically a stop, and every column is basically a trip. So you can basically go to a stop and then read off the times when the particular tram, when the trams pass by. And then if you change the data format, the layout from the previous very verbose one to this more smart representation that uses a matrix, you already gain a lot of space. So already, if you take this data, the stop text file, it's like 200 megabytes big, and you store these matrices, and then you only use as many bits as you would need to store minutes, and then you pack them all together in binary, it's like 10 megabytes big. That's like still too big, but I mean, it gives you some idea that really you can get a lot better. And then we have our own compression. We actually spent some time and said ourselves, okay, well, let's come up with some compression that makes this better. And we wanted to have compression where you don't actually have to decompress all of the data. Because if you have to decompress all of the data, then on the device, suddenly you have to store like 10 megabytes of data on the device for every feed, so that's too much. So we have a special compression that allows you to look into the data without actually decompressing the whole thing. It's like completely random access. And it's like very domain specific. And I don't really want to go into it too much, except to say that one way to think about that it's obvious that you could compress data, transit data a lot, is because the data is very regular. Like if you look at this matrix, then you basically said that between every column, the data is like monotonically increasing, right? So it's 21, 24, then always 10 minutes later. And then between every column and between every row, it also is monotonically increasing. Like between every stop to the next stop, it's always like 1 or 2 minutes. And often these differences are the same across a row or a column. So there's a lot of regularity, not a whole lot of entropy. So that's where our compression comes in, and that gets it down to 5% of the size of the schedules. So now we have compressed our numerical data, but now we have a bunch of structured data. So basically, if you have an app or something like this, and you say, okay, let's push some data onto the user, you'll probably also have not this weird schedule data, which is very domain specific, but you'll have a bunch of structured data, a bunch of tree data, like a database or something like this. And what are you going to do with that? At this point, this data is actually much larger than the schedule data. So we have to find a way to present it in a compact way if we want to send the data to the user at all times. So how can we store the structured data? Well, in order to make this discussion easier, I just want to talk about stops and not all of these other structures to be able to show this some stuff. So one way to store a bunch of structured data is to use JSON. I mean, it's pretty simple. Everybody uses it. That's also what the web service would use if you made a web-based app. And you could say that if you wanted to compress, well, it's not actually compress. If you just wanted to store the data, then all you would have to do is basically take out the data that you want to store, put it inside objects, and then use the JSON module in Python to store it. Note here actually that my compressor for the schedules is actually written in Python. So that's sort of what it would look like if I would use JSON. I would get an array of stops, take out the values I need, and then turn it into JSON. Right now, the values I got is like the name of the stop, its location, latitude, longitude. The code is like is a number that defines the stop, within some, for example, for the real-time thing to say, okay, for the real-time API so that it knows what stop it's referring to. There's some Boolean value that knows whether it's a station, and the service pattern ID is like some magical number that we come up with internally, because we need to know what services actually stop at a stop, like what routes, what schedules, and all of this stuff. So we have one magical number that does that. So problem with JSON is it's actually pretty big. So for the stops, it's like 2 megabytes, and sure it would compress a little, but there's just a lot of like stuff in there that keeps repeating, and it's sort of annoying. So JSON is great because it's easy to use, it is human readable, so it's easy to debug. It's self-contained, meaning that if you look at a JSON file, you can figure out what these values mean. You don't need to have a separate guide that says, well, this is the name of a stop, because you see that the structure is defined. So that's very convenient. The bad thing is that the files are pretty big. And then if you want to load the data, you also have to parse the data. So if you want to load megabytes of JSON, say you took quick JSON and then you compress the JSON because you need it smaller. So you have to decompress it, then you have to parse it. You have to store it in memory in some way, which is going to use up a lot of memory. And then it's all just going to be very slow. So one way to maybe turn into binary, but still keep what JSON does, is to use something called message pack. And message pack defines it, like they advertise themselves as saying they're like JSON, but fast and small. And message pack is almost like a drop-in replacement for JSON. So you can actually just tell message pack, well, here's a JSON, just turn this into binary, and it will. So here I have the code, which is basically the same as I had before. The only difference is, rather than packing it in JSON and turning it into a string, I just turn it into a message pack thing. So then, well, previously the JSON looked sort of like this. The message pack will actually create a bunch of binary gobbledygook. But if you look at the data, you notice that inside the data, you actually store all of the keys. There's name, latitude, longitude, right? The name, there's the name of the street, the latitude, and a bunch of binary data. That's probably the latitude and the longitude. So you basically keep storing all of these keys. Like we have all of this data in there. But it's like, but we wanted to save space. If we want to save space, we don't want to store the name and the latitude and longitude, those words, because we kind of we know what those things are. We know that there's a name stored, and we know that there's a latitude stored. So in message pack, you can actually use a custom encoding, a custom serialization. And the way you would do that is you would basically just go through all of the values that you're interested in and just drop them into a buffer. You would just tell message pack, okay, well, this is a string here, it's a name, and then add that to the end of the stream. And then you say, oh, well, this is a latitude, add that to the end of the stream. And it turns it into some binary thing, and then it just puts it in there. And then when you want to read out the data, you can do it again. You would basically say, okay, well, now the stops are coming, so how many stops are coming, right? So I actually wrote the length, the number of stops, so that when you read them out, you say, okay, I'm reading out this many stops. And then you read a stop, you just read them out in a reverse, right? You say, okay, well, first is the name, then the latitude, then the longitude, then the code, then the question whether it's a station or not, and then the service pattern ID value, and then it's the next stop. So this way, you basically have the same as before, except now you don't store a bunch of keys. That data is gone, right? So now basically the tool that compresses the data and the tool that reads the data, they have to agree on a format, right? They have to be written in tandem, because otherwise you're not going to be able to get your data back the way you wanted it to. So now the data looks sort of like this. Again, a bunch of binary gobbledygook. You see the name of the stops in there, but you don't see any of the keys. So in order to understand how this message pack actually works, it's actually a relatively simple and clever format. What they do is when they pack a particular datum or a particular value, they use the first byte to identify what is the type of this. And then, for example, if you look at the values, I turned all of the things that are not strings into hex values. The first byte is a B6, which actually signals to message pack that, well, this is a string that has the fixed length 22. So then the next 22 characters are the string. And then the next thing is the next number, which the next value, which is a float, which is defined by the CB value. So the CB value says the next 8 bytes make up a 64-bit floating point value. And then again, there's another 64-bit floating point value. The value 0, well, this refers to the integer 0. The value C2, that's a Boolean false. And then again, there's another 0. So this first byte, some of the values are just saying what the value is, like true or false. Some of them saying, well, there's an array coming up of values. You have to figure out what those values are. Some of them are saying this is a string. And if the string is short, it encodes inside the byte itself the length of the string. And then also for integers, you can store numbers up to like 128. And that byte actually knows, well, that's 100, that's that particular number, so let's say 64. It only uses one single byte. So it's a very compact representation. And it's actually relatively simple. So message pack is great because it's easy to use, and it's self-contained in the sense that if you look at a particular byte in the stream, you kind of know what type it has. But you don't know what semantically it is. I don't know, okay, I know it's a string, but you have to know elsewhere that it's a name. You have to have agreed beforehand that there's going to be the name of a stop, or the latitude, or the longitude. The representation is very compact, and overall it's great for small messages. But if you consider that you might have megabytes of data and you want to load it inside a mobile application, and you load it and then you have to parse it, and then you have to store it inside some sort of memory representation, because you first need to parse it, then store it in the memory in order to be able to access the data, that may still take a fair amount of time. So once your data gets too large, it may not be so great. So it's not really the best for sort of large structured data. It's very great for like small messages that you send to people. Oh, and by the way, we went from the JSON, did I say that before? Right, so the JSON was about 2 megabytes, sorry. When you store it as a binary JSON, it's a bit more than a megabyte, and then when you remove the keys and have your own fields, it's about 600K, and that's where we're at right now. So one project that tried to solve this problem is a project called Captain Proto. We almost used Captain Proto, but when we started looking into compressing feeds like 2-3 years ago, that had just come out, and I think it came out on April 1st, and it looks a little bit silly, but it's actually a really good library. I'm not quite sure why they make that serial joke. It's not conflicts. Anyway, so what Captain Proto does, it provides another way of creating binary files. So it's made by the people who made protocol buffers, if anybody has ever heard of that. So it's like the next generation. The idea of this format is that the format that's used for interchange that's inside the files is the same as the in-memory representation. So basically all you have to do is when you want to load a Captain Proto file is you take the file, you load that into memory and tell some sort of library that relates to Captain Proto, well, this is now my Captain Proto file, and it can start interpreting the data inside it without copying it elsewhere, without deserializing it. So the way it works is sort of like using C structs. And so it uses structs, data that's packed inside memory sitting next to each other, and it uses pointers to create structure that is like a tree. And the pointers are not in absolute terms to addresses in memory. No, of course, they're relative to the file itself. So if you know where you are in the file, you can have, say, well, this is some other data, and it's at this particular address relative to the file itself. So one point is that Captain Proto is like C structs. So in order to work with these C structs, they use something called schemas, where we define what these files look like. So for example, I defined a schema for the stops, and it actually kind of looks like C-ish in a way. So the file is relatively simple schemas. You have some ID in the top that you always have to put there. I think it's to make sure that the files have the format that you expect. Then you could define, structures, and here I defined a struct that's a stop. And then you basically have to give it a name and a type. So there's a text type that's a name, and then there's two floating point values at the latitude and the longitude. And there are all our values again. And you also have to give it an index. You have to number the fields through, because you can actually later add new values in the end, and they will still be sort of compatible. Like all the versions of the library will still be able to read these things, as long as the order of the fields that were there before stay the same. So you can always add things in the end. It's kind of convenient. So you might have a struct referring to the stop, and then a list of the stop. And when you have a schema like this, in all sorts of languages with Cap and Proto, there's a tool called capn, where you can generate like a C++ library that allows you to read these particular files. In Python, we can use these schemas directly. It sort of looks like this. So you import capn p, the Python module, and then you import the stops capn p, which is basically this schema file here. Like the capn p module, it has some sort of import hook that overrides imports, and it looks for this underscore capn p just to load the schema. And then basically, all of a sudden, this now becomes like a module. So if you want to pack a particular stop, you just say, stops capn p, that's the module where that is associated with the schema, create a new stop with, say, new message, and then you assign all of these values to it. You can even also just take the stop and just assign more values to it. Oh, my thing is cut off. Oh, no, it works. So then when you want to pack all of them, you basically do the same thing for all of the stops. You just say a new message, and you assign the values that are the list of stops that you create. And the way you actually then turn it into an actual binary file is to just take the resulting object, the resulting proto object, and you just write it into a file using the write method. That's pretty simple. So the way the data looks like, I don't know, it's kind of hard to interpret at this point. It's really just a bunch of binary gobbledygook. But one thing to note is that I put the whole data file there, and I put the beginning and the end. And actually, the strings, they end up in the end of the file, because what it does, it creates structs. And then when it has to refer to a string, because a string has not a fixed length, it stores a pointer. And then the pointer refers to the strings that are then stored somewhere in the end of the data. So basically, in the beginning, you have a list of structs with pointers to strings towards the end of the file. One thing to notice, there's a lot of 0 bytes floating around. So the size is actually much larger than the message pack. The message pack was, what, 600K, and now we're back to almost a megabytes. But given that these values are all 0, you can always gzip it. So if you send it over the network, you can compress it in some way, and it probably will end up the same smaller value. So the encoding for Cap'n Proto is actually pretty smart. It also uses a tree structure. But one thing I sort of didn't like so much is that every struct has a header that's like 64 bits, and every pointer is also 64 bits. That seems like a bit of a waste. But the format is incredibly powerful. It includes features guarding against attacks. So it doesn't just point to some raw data in memory. It uses it to read the data, but it's like the Cap'n Proto object will refer to the data, but when you read on it, it will actually make some checks to make sure that there's no malicious data, that it doesn't point to outside of the file that you've loaded into memory, so that you can't snoop. You can't create a malicious file that snoops onto memory that doesn't belong to the file. Yes, there's also something that's smart in that if you have a bunch of different values that have different sizes, like an int64 next to a byte, and then an int16, it will try to arrange them in a way that will make the padding smart. Yeah. So another format that I really can't get into because I don't really have a lot of time is something called flat buffers. And it was developed by Google to store assets for games. It's maybe something that I would use nowadays. It's a bit more bare bones than Cap and Proto and gives you a little bit more control, but also it gives you less powerful features. And again, it uses a struct-like representation and schemas to track the data. So when I looked at these options, and they didn't really exist, and flat buffers didn't exist when I was writing this, Cap and Proto was incredibly new. I didn't like this idea of having schemas. When I was using JSON, I could just dump a bunch of data into a JSON and say, well, those are my stops. Why do I have to have a separate file with all these definitions? You know, I'm a friend of Python. I like my things to be typed, but I don't want to declare things. And when I was thinking about how much data there's in stops, there are so many fields. It seemed like crazy to define all of these things manually. And also I wanted to have more control over my bits. Like I wanted to really have bit level control of my data. So I was thinking, well, why don't I just use actual C structs? Why do I use some library on top of that? And it seems kind of silly nowadays, but you know, this actually is possible. And you can actually use bits and to decide what every single byte of your file is. And you can use the struct model in Python. So the struct model is actually a module that allows you to interchange data between Python and C. And I think it's more used for like libraries talking to each other, or maybe to parse an odd message coming from the web. I don't think it's really meant to be used for like large file formats, but you could use it for it. So you could have something where, you know, like you import a struct, and then with struct there's the pack method. You should just give it a type and a value, right? So, you know, it's an integer. You store some number, and then you can store a byte, and you can store a character. And then they will return strings, so you can add them together, and then you have that one string. So it's like, it should be 7 bytes, right? So 1, 2, 3, 4, 5, oh no, it's 6 bytes because this is a byte. So 1 character, 1 byte, and 1 4-bit integer. So, well, I have exact control over all of my bytes. Hey, that's what I want, right? It seems kind of inconvenient the way I have to define them. So I thought to myself, well, I'm just gonna write a little helper library. My little helper library turned out to be kind of large, and I just called it named struct because all I wanted is names inside the struct. So I just developed this on top of structs, and it allows me to have schema-less files that are nevertheless typed. So the types are just specified just like in the struct module when creating the data. So then when I create a stop, all I do is I go to the named struct module and I say, well, give me a struct, and I give the struct a name. So if I give the struct a name, it suddenly has sort of a type that I can refer to. That name becomes its type. And then I can just basically add things to it. So the library is not very Python looking. I'm kind of sorry. I'm kind of still stuck in the Java world with my naming convention. Don't pep-8 me. So I'm also using chaining. This is also very not Pythonic. But you don't have to use chaining. You can also just create the struct object and then add a value to it. So every time I say add string, which that's the type, that's the string, I give it a name, which is called name in this case. I give it a value, which is basically the value of the stop, and then here, well, what's this reference bit width? So that's my idea of having complete control over my bits. And the way I have well, the thing is that even when you have a string, it may have a variable length. So it can't be stored inside the struct. It has to be stored somewhere else. So actually what this creates is a pointer to where the string actually resides. And since I have a very tree-like structure, the string is going to be stored just after the struct inside the memory. So since the struct is really small, I know that the offset from the struct to the data only needs to be 1 byte big because the struct is small. I don't need values bigger than 256. So that's what I did. I just created a reference bit width of 8. So now all of a sudden I have an 8-bit pointer. Well, you can't do that in Cap and Proto. All of the pointers are 64 bits. In my thing, then I store the latitude and the longitude in the code and the service pattern ID, and I store them as either signed or unsigned integers. Note that the latitude and longitude, I store them as integers because I don't have floats. I figured in a serialization format, I don't really want to store raw floats because I'm not sure exactly whether everybody's going to use the same format. If it's integers, everybody's using little endian integers nowadays, so I can just dump that in there and then I can read that. So I just converted them into integers. It's kind of cheating as well because I'm turning a double, which is 8 bytes, into an integer, which is 4 bytes, but you know, it's compression right there. So now I have this little struct created, and then when I create for every stop, I can just create an array of these things and create another struct that is all of the stops. So it's similar to Cap and Proto, but I don't have a separate schema. The schema is implied by the code because I put values and I put types at the same time. So one little thing that I can do with this now is I can print out once this pack stops. So the pack stops function gives me one of these name struct objects. So if I give the data out there, it tells me basically what values and what types does it have. So the pretty function gives me an idea to look at these things. So I see right at the top there's a list of stops, and the first stop, at the first thing, it has a reference, sorry, it's a list of references that does all the stop, then every single stop is a struct here that starts there. Sorry, I didn't do the indentation properly. This is one stop. And you see that the first thing it does, there's a reference 8, like an 8-bit pointer to the string, which will be stored just below the struct. And then there's a bunch of padding bytes, and the padding, there's this station Boolean flag, and then there's a bunch of padding bytes because everything needs to be aligned properly because you're actually reading it as C structs. You don't want to have misaligned data. So these get added in as necessary. So I can look at the pretty output to see what it is, and also I can generate a C header from that. So because the file object is the schema, that's where I generate my code from. So from that data object, I generate my header file generation, my header file, and that is actually used on the device inside the app. It's a C++ code to read the data coming in. And in order to be able to do this, you use this attribute pack thing, but it actually works. I might be like violating some aliasing rules, but I've done a bunch of testing and it all sort of works out. And then of course, you can also just generate the binary blob. So that's what I do with pack. And then I have my binary blob file, and now the file is about 600K, which is smaller than the Captain Proto, that was 900. Further, I developed this thing further because it just seemed so wasteful to have all of these, I have an int32 when most of the time the values may be much smaller. So I created a bunch of things that uses bit fields and bit field arrays and all of like little things to make it smaller. Too bad I can't get into it. But I thought there was a whole bunch of cleverness there. And then also at some point I decided that, well, those strings are annoying. If you want to have a compressed file, you might as well actually compress it using gzip, because gzip works well with text. So I separated all of the names, and I separated all the numerical data, and I stored them in separate things. So then the compressed strings are about 100 kilobytes. There's also something in there that makes it very fast to search for names. And then in the end, I ended up with 200 kilobytes. And I could do this because I have complete control over all of my bits. So then in the end, I have about 200 kilobytes using all of my bit magic and hacking. And the JSON was 200 megabyte, message pack was 600K, and Captain Proto was 900K. Presumably, if you actually use a very strong compression, those differences will get a bit smaller. So the idea that we used in the end is that we have this binary file where the in-memory and the in-file structure is the same. That worked really well. That works also in Captain Proto and flat buffers. Our representation is much more compact than them. And the schema is separate. It's not separate. It's in the code. And then you can generate it directly from objects. This turned out to be a little bit of a liability because once your file gets really, really large, you need to have a feed that exhibits all of the possible fields that you have, because when you generate the header file of it, it has to have everything in there. So what ended up happening is that we created a special fake feed that we used as part of our integration testing that exhibits everything. And that means that in order to have a schema, we have this fake feed, we have our compression, then we generate the header file, the parsing library from that once we've generated the feed. So in the end, it's a bit of a pain. I think that actually schemas is the way to go. I mean, it kind of hurts me to say, also as a Python person, to having separate declarations seems annoying and it's maybe more time consuming, but at the end, it's much more easy to maintain. So my story in the end is, well, I figured out a bunch of bits and it's fun, but maybe it's better to stick with something that somebody's written like Captain Proto or flat buffers and be happy that you have schemas. Overall, though, our binary format thing was very much a success. I mean, we have the schedule on the device. I think we're the only transit app that actually has offline schedules just like that. And we could do like offline routing if you wanted to. You could do all sorts of things. Yes. So I think that's basically it, what I have to say today. So thank you very much.
Thank you, Anton. We have 3 minutes, 3.5 minutes for questions. Please.
You talked a lot about the data, the schedules. How do you bring the map to your app?
How do I what?
The map, the roads.
The map, or is it just Google?
That's Google. Oh, okay.
But Google, once you start looking at it, it will cache data as well. So if you go to a city and it loads the feed and it starts downloading the map, then you get the map. But it's true, if I was in London and then I get the gray map because it doesn't have the map, but I have the schedule, great.
So, if I understood correctly, the name struct data format is a record-oriented format.
Is what?
A record-oriented, one record after the other.
Yes.
Have you tried to experiment with column-oriented serialization, where for a specific attribute you have all the values packed the one after the other, like parquet, for instance, and to benefit from better compression in that case?
So what I ended up doing in the end is using bit fields. When I know that I have data where I know that I'm not using 32 bits, I started using bit fields. So in bit fields, you don't align data to byte boundaries anymore, you have bit values. So you might have a record with 5 values, and one has 13 bits, and one has 16 bits, and one has 18 bits. But you don't know how many bits you will have a priori. You can't define this statically, because it depends on the data. So what we created something where there's a small header file that defines how many bits every field takes and how many fields there are. And then it's just records of these data, where the records might take 27 bits that are like 8 bits, 7 bits, and 9 bits, or something like that. And that works really well, and it's completely random access. And whether you store it as a list of records or just all of them individually, I don't think it really makes a difference. But we did do this, and that's what I mentioned when I got down to about 200 kilobytes. That's basically what I used. And I kind of hope that this sort of format makes it into Captain Proto as well, or flat buffers, because it makes things much smaller. You don't have a bunch of zeros everywhere. Yeah.
One more last question. 10 seconds long, no longer. Nobody? Thank you, Anton, very much.
Thank you very much.